Okay, so time for mathematical formulae and data and tables. So, opening up with pi. Pi is approximately 3.14159265358462384626433. And it's the circumference of a circle divided by its diameter. E, the next number to consider is E, which is 2.7188284590452353600287. And it is the natural base of logarithms. It is the limit as n approaches infinity of 1 plus 1 over n, all to the power of n. So what does that mean? Well, consider 1.5 raised to the power of 2. Then 1 1/3 raised to the power of 3. Then 1 1/4 raised to the power of 4, and so on and so on. As you type that in on your calculator, you will notice that it heads towards a particular limit, and that limit is the number e. The square root of 2, that's approximately 1.414213562, and people interpret it as the length of the diagonal of a unit square. So picture a square whose sides have a length of 1, then the diagonal of that square is approximately 1.4, but it's precisely the square root of 2. The square root of 3 is 1.7320508, and this can be found in a right-angled triangle or right triangle with a base of length 1 and an altitude of 2. Wait, did I get that right? Let me just think. Oh no, I got that. Okay, I understand. Okay, so if the base of the right triangle is 1 and the altitude is root 3, then applying the Pythagorean theorem, we square the 1 and square the root 3, and then we have 1 add 3, which is 4, and then the square root of that is 2. So that produces the familiar triangle, the familiar right-angled triangle whose base is 1, whose altitude is the square root of 3, and whose hypotenuse is 2. That's where the square root of 3 appears. The square root of 5 is 2.2360679774997896964. And the square root of 5 appears when calculating phi, or the golden ratio, which is 1 plus the square root of 5, all divided by 2. That number itself is rather special, and it's about 1.618. And okay, others here. The cube root of 2 is 1.25992, and the fifth root of 3 is 1.24573. So these are both very close, and they're both close to 1 1/4 or 5/4. The next pair that I want to mention are e to the pi and pi to the e. It's often a question people think about: how can I prove which one of these is larger? The answer is in fact e to the pi. E to the pi is 23.14. So that's quite close to pi plus 20. Whereas pi to the e is 22.459. E to the power of itself, as in e to the e, is 15.154. Some other special ones to mention are logarithms. There are natural logarithms and common logarithms that people become familiar with. The common logarithm is logarithm base 10. So, for example, the common logarithm of 1000 is 3. This may also be read aloud as log base 10 of 1000 is 3. And it answers the question, to what power must I raise the number 10 in order to get 1000? Log base 10 of 2 is 0.301. And notice also that 2 to the power of 10 is 1024, which is very close to 10 to the power of 3. And this is quite handy for estimating the order of magnitude of powers of 2. For instance, 2 to the power of 42. I might not know exactly what that is, but I know that it will be 10 to the power of 12 and then multiply by 4 approximately. So around about 4 trillion. So that was log base 10 of 2, which is 0.301 approximately. Log base 10 of 3 is 0.477. Log base 10 of e is 0.434, which makes sense, as e is between 2 and 3. It's 2.71828. And lastly, log base 10 of pi is 0.497. And then there are natural logarithms. So we might just say that the natural logarithm of 10 is 2.30258. And the natural logarithm of 2 is very important because this features in half-life calculations. The natural logarithm of 2 is 0.693, approximately. And the natural logarithm of 3 is 1.0986. A special constant is Euler's constant, which is symbolized by gamma, and is approximately 0.57721, 56649, 01532, 86060, 6512, and so on. how to think about this number, though. Well, if you add 1 to 1/2, and then add a third, and then a quarter, and then a fifth, and a sixth, and a seventh, and so on, that's a very, very slowly growing sequence. A very, very slowly growing sequence. But as you continue to add on more and more terms, it actually does diverge and shoots off towards infinity. But it grows incredibly slowly. In fact, there's a name for these numbers. They're called the harmonic numbers. One is the first harmonic number, then 1 plus a half is the second, then 1 plus a half plus a third is the fourth, and so on. Now, an interesting question arises when you ask, for example, what happens when I consider the 10th harmonic number minus the natural logarithm of 10? You seem to get a number that is a little bit less than 1. Maybe it's around 0.6-ish. And as you increase n in this consideration, like the 100th harmonic number minus the natural logarithm of 100, you get closer and closer to this number, Euler's constant, which is about 0.57721566649. And so it's the limit of that as n tends to infinity. Really, it's the difference between the continuous and the discrete, in a way. But not a lot is known about this number. E to the gamma is 1.78107, and the square root of E is 1.64872. The square root of pi is the same as the gamma function of a half, and that evaluates to approximately 1.77245. The gamma function is a continuation of the factorial function. The factorial function sort of has its origins in asking how many ways I can rearrange items on a bookshelf. So 4 factorial is 24, and it's 4 times 3 times 2 times 1. And that's how many ways you can arrange 4 distinct books on a bookshelf, for example. As for 5 factorial, that's 5 times 4 times 3 times 2 times 1, which is 120. But what about the question, what is 4.7 factorial? Well, this obviously doesn't make much sense, as there's no such thing as 4.7 books on a bookshelf. But in the same way that we are able to make sense of the sentence that the average family has 2.2 children, there's a way to make sense of 4.7 factorial, and it's through the gamma function. This has nothing to do with Euler's constant, which is a lowercase gamma. The gamma function is spelled with an uppercase gamma. The gamma function of 1/3 is about 2.67893, and the gamma function of a quarter is about 3.62561. Another constant that's worth mentioning is the radian. The radian is found by thinking about the circumference of a circle and thinking about an arc on the circumference that's as long as the radius of the circle, and considering that to be a unit of turn. Now, because 2 pi copies of the radius of the circle fit into the circumference of the circle. In other words, a circle has a circumference about 6.28 times longer than its radius. Because of this fact, the radian must be quite a precise figure, and you can't really make a full turn using a whole number of them. A radian is about 57.3 degrees, and about 6 of them are required to make a full turn, but to be precise is about 6.28. But no whole number of radians will ever make a whole number of turns, because pi is irrational. Finally, 1 degree is about 0.0175 radians. So those are special constants. There are many others. And indeed, if you think about it, pi is the circumference of a circle divided by its diameter. But why couldn't we have said, or came up with a constant, which was the diameter of a circle divided by its circumference, or perhaps the radius of a circle divided by its circumference? And so each constant really has several others buried inside it because of these arbitrary choices. And you may actually spot this out in the wild when you look at mathematical formulae and you see 2 pi, for example, or you see 1 over pi. Now, I want to read through some special products and factors. The first is the square of x plus y. That is x squared plus 2xy plus y squared. Then the square of x minus y, which is x squared minus 2xy plus y squared. Notice it's just the middle term which changes sign. So I'll read those out one more time. X plus y all squared is x squared at 2xy at y squared. And x minus y all squared is x squared minus 2xy plus y squared. This pattern persists for higher powers of sums and differences. X plus y all cubed is x cubed plus 3x squared y plus 3xy squared plus y cubed. And x minus y all cubed is x cubed minus 3x squared y plus xy squared minus y cubed. Notice the plus minus pattern. X plus y to the 4 is x to the 4 plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the 4. Notice the symmetry of the terms. The first observation we make is that there are 5 terms after raising x plus y to the power of 4. That observation is a valid one. If we were to raise x plus y to the power of 10, then the output would have 11 terms. For x plus y to the 4, the terms are arranged such that x is descending in powers, starting at 4 and going down to 0, and y is ascending in powers, starting at 0 and going up to 4. So I'll read this one again. X plus y to the 4 is x to the 4 plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the 4. The last observation is that the numbers in front of the terms, which are coefficients, follow a symmetric pattern, 1, 4, 6, 4, 1. This is intuitively sensible because x and y are playing more or less equivalent roles. For x minus y to the 4, we have x to the 4 minus 4x cubed y plus 6x squared y squared minus 4xy cubed plus y to the 4. So again, we see the plus minus pattern. For x plus y to the 5, the coefficients are 1, 5, 10, 10, 5, 1. And for x plus y to the 6, the coefficients are 1, 6, 15, 20, 15, 6, 1. These are all special cases of the binomial formula, which enables you to add a pair of terms and raise them to an arbitrary power. For example, x plus y to the power of 17. We also have patterns for differences of perfect powers. For example, x squared minus y squared. This is x minus y times x plus y. And it's known as the difference of two squares, which is a sensible name as both x squared and y squared are squares. And by subtracting one from the other, I'm considering their difference. So x squared minus y squared, which is equal to x minus y times x plus y, that's the difference of two squares formula. There is also a difference of two cubes formula. X cubed minus y cubed. This is x minus y all times x squared at xy at y squared. As for the sum of two cubes, x cubed at y cubed, that's x at y all times x squared minus xy plus y squared. So let's hear those two again, side by side. X cubed minus y cubed is x minus y all times x squared plus xy plus y squared. And x cubed plus y cubed is x plus y all times x squared minus xy plus y squared. Are there similar patterns for the difference of 2/4 powers and the difference of 2/5 powers? There are indeed, but there does not appear to be any such pattern for the sum of 2/4 powers, in the same way that there's no pattern for the sum of two squares. The odd powers are special. So, what is the pattern for the difference of 2/4 powers? X to the 4 minus y to the 4. This is x minus y times x plus y times x squared at y squared. But why is this the case? Because a fourth power is actually a square in disguise. So x to the 4 minus y to the 4 is the same as a squared minus b squared, if I let a stand for x squared and b stand for y squared. And then using the difference of two squares formula from earlier, it becomes a minus b times a plus b, which in this case means x squared minus y squared all times x squared plus y squared. And then we notice that the x squared minus y squared is another instance of the difference of two squares. So we can break it down again. So, to reiterate, x to the 4 minus y to the 4 is x minus y times x plus y times x squared plus y squared. The difference of 2/5 powers and the sum of 2/5 powers don't exhibit an obvious and interesting pattern. But nonetheless, here they are. X to the 5 minus y to the 5 is x minus y all times x to the 4 plus x cubed y plus x squared y squared plus xy cubed plus y to the 4. Whereas x to the 5 plus y to the 5 is x plus y all times x to the 4 minus x cubed y plus xy squared. Let's just do that one more time. X to the 5 plus y to the 5 is x plus y all times x to the 4 minus x cubed y plus x squared y squared minus xy cubed plus y to the 4. Now, upon hearing those aloud, there actually does appear to be a pattern. we notice that the powers of x and y must always add to give 4 for the difference of 2/5 powers in the larger bracket. We notice that the leading bracket is x minus y, and when it comes to the sum of the 2/5 powers, the leading bracket is x plus y, and they exhibit the plus minus pattern. So generalizations could be found. We also note that for even powers, as in like x to the 10 minus x to the 10, we can express this as a difference of 2 squares. There's just one more special case to mention here, and that is this beautiful factorization of x to the 4 plus 4y to the 4. Although we cannot factorize a sum of 2/4 powers, we can factorize x to the 4 plus 4y to the 4. And it is, in the first bracket, x squared add 2xy add 2y squared. And in the second bracket, x squared minus 2xy plus 2y squared. You can hear that the only difference between those two brackets is a sign difference of the middle term. There are some generalizations that are possible, but something to look into next is the binomial formula and the binomial coefficients. The factorial was defined earlier, that n factorial is 1 times 2 times 3 all the way up to n. In other words, it's the product of the first n natural numbers. The factorials listed are 1, 2, 6, 24, 120. That's the first 5 factorials. The next 5 factorials are 720, 5040, 40,320, 362,880, 3,628,800. 0 factorial is defined to be 1. The binomial formula enables you to calculate the nth power of x plus y. It makes sense that the beginning and end would be x to the n and y to the n. But what about the interior terms? Immediately after x to the n comes nx to the n minus 1 y. But this is somewhat unsatisfactory. So I will say this, that the fourth term has something which takes care of the coefficient, something which takes care of the x, and something which takes care of the y. 3 parts. What takes care of the y? y cubed, because it's in ascending powers of y. What takes care of the x? X to the n minus 3, because it's in descending powers of x. And what takes care of the coefficient? A fraction. A fraction which is the product of three things divided by 3 factorial. And those three things are n times n minus 1 times n minus 2. So based on that, let's predict what the 7th term would be. It would have 3 parts to it. One part to take care of the coefficient, another part to take care of the x, and another part to take care of the y. What takes care of the y would be not y to the 7, but instead y to the 6. And what takes care of the x would be x to the n minus 6. And what takes care of the coefficient? It would be a fraction. Now, as we're thinking about the 7th term, it would be a product of 6 things over 6 factorial. And those 6 things will be n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5. This binomial formula can be extended to other values of n. There's a more convenient way to actually express this, and that's using the choice function, which is written using column vector notation, n on top and k on the bottom. And we read it out loud as n choose k. For example, 5 choose 2 is 10, and it's the number of ways that you can choose 2 fingers from the 5 digits on your hand. 2 digits from the 5 digits on your hand, rather. So, with that, how can this binomial formula be rewritten? Well, for x plus y to the n, we still have this structure which goes x to the n, y to the 0, x to the n minus 1, y to the 1, x to the n minus 2, y to the 2, x to the n minus 3, y to the 3, and so on. But the coefficient terms from before are now conveniently expressed as n choose 0 for the first term, n choose 1 for the second term, n choose 2 for the third term, n choose 3 for the fourth term, and so on. All the way up to n choose n. And by thinking of it in this way, the symmetry of the coefficients make a lot more sense. Earlier on, for x plus y to the 5, they were read aloud as 1, 5, 10, 10, 5, 1. And for x plus y to the 6, they were read aloud as 1, 6, 15, 20, 15, 6, 1. This symmetry now makes a lot more sense. Consider, for example, n choose 2. Why is this the same as n choose n minus 2? For n that's bigger than 2, of course. The reason why is because the number of ways you can choose the number of ways you can choose 2 items from n is the same as the number of ways you can not choose 2 items. In other words, how many ways you can choose all the remaining items. The coefficients are unsurprisingly called the binomial coefficients. And n choose k is the same as n choose n minus k, as stated earlier. The formula for n choose k is n factorial over n minus k factorial times k factorial. For example, with 5 choose 2, that would be 5 factorial over 3 factorial times 2 factorial. So that would be 120 over 12. 120 over 12, which is indeed 10. Now, there are some other properties of binomial coefficients to know about, and I'll just say some of them. In just a moment. The first is n choose k plus n choose k plus 1 is n plus 1 choose k plus 1. For example, 10 choose 3 plus 10 choose 4 is the same as 11 choose 4. Another example, 20 choose 6 plus 20 choose 7 is the same as 21 choose 7. This relationship gives rise to Pascal's triangle, or Pascal's array, which pops up in so many places. The next relation to talk about is that the rows of Pascal's triangle add up to 2 to the power of n. So n choose 0 plus n choose 1 plus n choose 2 all the way up to n choose n. This adds up to 2 to the power of n. For example, 3 choose 0 plus 3 choose 1 plus 3 choose 2 plus 3 choose 3. Well, that would be 1 plus 3 plus 3 plus 1, which is indeed 2 to the power of 3, which is 8. Another pattern to notice is that if you do the plus minus pattern on the rows of Pascal's triangle, In other words, n choose 0 minus n choose 1 plus n choose 2 minus n choose 3, and so on, all the way up to n choose n. Then this evaluates to be 0. For example, 1 minus 4 plus 6 minus 4 plus 1. This evaluates to 0. Another pattern to see, and this is a pair of patterns, is that n choose 0 plus n choose 2 plus n choose 4 plus n choose 6, and so on, evaluates to the same thing as n choose 1 plus n choose 3 plus n choose 5, and so on. And they both evaluate to half of 2 to the n, which is 2 to the n minus 1. A kind of interesting pattern is that n choose n plus n plus 1 choose n plus n plus 2 choose n plus n plus 3 choose n, and so on, all the way up to n plus m choose n, comes to n plus m plus 1 choose n plus 1. Lastly, what would happen if I were to square the entries in a row in Pascal's triangle and add them together? So the square of n choose 0 plus the square of n choose 1 plus the square of n choose 2 plus the square of n choose 3, and so on, all the way up to the square of n choose n. In that case, I would get 2n choose n. For example, the square of 3 choose 0 plus the square of 3 choose 1 plus the square of 3 choose 2 plus the square of 3 choose 3 would be 6 choose 3. And when we calculate that, it would be 1 plus 9 plus 9 plus 1, which is 20. And indeed, 6 choose 3 is in the row that goes 1, 6, 15, 20, 15, 6, 1. And 6 choose 3 is right there in the middle. There's an extension of the binomial formula, which is called the multinomial formula. Although it's quite involved. Next, we'll look at some geometric formulae. The first is a rectangle. For a rectangle of altitude A and a base of length B, the area is A times B. In this instance, happily, both of those two letters make sense. A for altitude and B for base. And of course, the perimeter is 2A plus 2B. For a parallelogram, with an altitude of h and a base of length b and a slanted height of a, the area can be computed as b times h, the base times the altitude, just like the rectangle. Or it can be computed as AB times the sine of theta, where theta is the angle between A and B, the two sides of the parallelogram. And the perimeter of a parallelogram is, of course, 2A plus 2B. For an arbitrary triangle with an altitude of h and a base of b, its area is known to be half bh, or half of base times height. A more famous area rule is half AB times the sine of C, where C, or big C, is the angle between the sides A and B. But there's another formula that's very useful called Heron's formula. And as long as you know the three sides of the triangle, the lengths of the three sides of the triangle, you can obtain the area of the entire triangle. First, the semi-perimeter is half the length of the perimeter of the triangle. In other words, A plus B plus C, all divided by 2. Let's call the semi-perimeter S. Then Heron's formula states that the area of an arbitrary triangle is S minus A times S minus B times S minus C times S, all square rooted. We can confirm that this works for the classic 3, 4, 5 right triangle, whose area is known to be 6. The semi-perimeter of the 3, 4, 5 triangle would be 6. And so we would multiply 6 by 3, then by 2, and then by 1. And so we would obtain 36. And then we have to take the square roots, and we get 6. So it works for that triangle. And it goes without saying that the perimeter of the triangle in question is A plus B plus C. Now, for a trapezoid or a trapezium, there are several quantities involved. The altitude is h, and the two parallel sides are A and B. And from this, we know that the area is half of the height times the sum of the two parallel sides. Or if you like, it's the average of the two parallel sides multiplied by the height. As for the perimeter, well, visualize the trapezium as having a base of B, and that being the longer of the two parallel sides, and a top side of A, and two angles at the bottom, being theta, or rather being alpha and beta, then the perimeter is A plus B plus the height multiplied by the sum of the cosecants of those two angles. So find the cosecant of alpha and the cosecant of beta and add them together and then multiply that by the height and then add on A plus B. And then you'll get the perimeter of a trapezoid or trapezium. But what about a regular polygon with n sides, each of a fixed length b? For example, a pentagon whose sides all have a fixed length, like 10. Is it possible to find the area of such a polygon? It is. The area of such a polygon is 1/4 times the number of sides times the side length squared multiplied by the cotangent of pi over the number of sides. So here's a specific example. Let's consider a hexagon with sides of length 7. To work out the area of this hexagon, which has 6 sides, each of length 7, what you would do is 1/4 times 6 times 7 squared times the cotangent of pi over 6. Let's hear that one more time. It would be 1/4 times 6 times 7 squared times the cotangent of pi over 6. And so it pays to know special values of the cotangent function. Now, for a circle with a radius of r, its area is famously known to be pi r squared. For example, if it has a radius of 7, then the area is pi times 49, or 49 pi. And the perimeter is 2 pi r. 2 pi r. So in this case, it would be 14 pi. For a sector of a circle, or what you may think of as a cake slice of the circle, the area is half r squared times theta, where theta is the angle of the sector in radians. For example, imagine that the sector was of a circle with a radius of 7, and the angle of the sector was pi over 6, or 30 degrees. Then what you would do is a half times 7 squared times pi over 6. So that's a half times r squared times theta. And the arc length of the sector is just the radius times the angle. The radius times the angle, r theta. So in this case, it would be 7 times pi over 6. 7 times pi over 6. Now, there are two rather beautiful formulae coming up, and that's the radius of a circle inscribed in a triangle and the radius of a circle circumscribing a triangle. For a circle inscribed in a triangle of sides A, B, and C, the radius is the area divided by the semi-perimeter. The radius is the area divided by the semi-perimeter. And the area can be worked out using Heron's formula from earlier. As for the radius of a circle circumscribing a triangle of sides A, B, and C, the radius of that circle is the product of the lengths of the sides divided by 4 times the area. And this is a rather beautiful fact. So I will just reiterate those two. The radius of a circle inscribed in a triangle of sides A, B, and C is its area divided by its semi-perimeter, whereas the radius of a circle circumscribing a triangle of sides A, B, and C is the product of its sides divided by 4 times its area. So in both cases, the area is involved, but in the first case, for an inscribed circle, it's on the numerator, and for the circumscribed circle, it's on the denominator. And for the circumscribed circle, we have the product of the sides on the numerator, whereas for the inscribed circle, if you think about it, on the denominator, we have the sum of the sides. Admittedly, it's half of it, though. Now, for a regular polygon with n sides that's inscribed in a circle of radius r, we have an expression for the area of this polygon. It's 1/2 times n times r squared times the sine of 2 pi over n. So, for example, for an octagon and for a circle with a radius of 11, the area of that octagon would be 1/2 times 8 times 11 squared times the sine of 2 pi over 8. So that's 1/2 times 8 times 11 squared times the sine of 2 pi over 8. Whereas the perimeter is 2nr times the sine of pi over n. So for the octagon with sides in a circle of radius 11, its perimeter would be 2 times 8 times 11 times the sine of pi over 8. The other case to consider is a regular polygon of n sides circumscribing a circle of radius r. In that case, the area is nr squared times tan of pi over n. For example, let's say a hexagon is surrounding a circle with a radius of 29. Then the area of that hexagon would be 6 times 29 squared times the tan of pi over 6. That's 6 times 29 squared times the tan of pi over 6. And as for the perimeter, well, that would be 2nr times the tan of pi over n. So in this case, 2 times 6 times 29 times the tan of pi over 6. There's quite a bit of symmetry in those formulae, except one uses the sine function and the other uses the tan function. Just a few more formulae here to mention. For a segment of a circle which has a radius of r and a segment which has an angle of theta, you can imagine that it cuts off a cap of the circle. The area of that cap is half r squared multiplied by theta minus sine of theta. Once more, it's half r squared times theta minus sine of theta. The last one to mention here before we pause is an ellipse. An ellipse is kind of like a mathematically precise and fancy oval. You can imagine that it has a center. It can be constructed by putting 2 drawing pins in a cork board, creating a loop around a pencil and drawing it tight around those 2 drawing pins, and then using them as a kind of makeshift needle of a compass. It's a little bit hard to visualize, but if you were to do that, you would trace out a kind of oval, which is called an ellipse, because of the way that it's constructed. It would have instead of 2 radii, it would have a semi-major axis and a semi-minor axis. The semi-major axis is usually called A, and the semi-minor axis is usually called B. Now, the area of an ellipse is conveniently pi times A times B. That's just like pi r squared, except in this case, instead of being pi times r, it's pi times A times B. As for the perimeter of the ellipse, this is actually an open-ended problem. It's not known exactly what it is. It's not known to have a closed form. But approximately, we would expect it to be 2 pi multiplied by some number involving a and b. And indeed, approximately, it's a half of the sum of the squares of a and b, square rooted, then multiplied by 2 pi. So that's a squared plus b squared over 2, all square rooted, then multiplied by 2 pi. But there is a precise integral for it. Now, we're going to finish here and pause here for a moment, so be well.